Let's do a conservation of momentum and energy and springs all in one. Look at this. Okay, so what this picture is if you can imagine that there's a track. There's like an air track underneath this thing. And these carts, what they do is they kind of hover on this little pocket of air on the air track. And we can set the two carts in motion and they'll collide. Now there's nothing lost to friction. The only thing we have going on internally with this system is this spring attached to cart number 2. And we're given a picture that says, let's see, what's the end velocity of this cart? So we're told that this cart is now 3 meters per second going this way still. So that means that this cart is still going this way at some unknown velocity. So we can look at this first. The first question could be, what's the velocity of this cart? Then the second part that we'll figure out is how far does that spring compress at this snapshot in time? So when this cart is going 3 meters per second still this way, and this cart is still going that way. So let's see. In terms of momentum, if I define this direction as positive, then I'll have mass 1, velocity 1, minus, because it's going this way, minus mass 2, velocity 2, is going to equal, let's see, mass 1. Is this a combined mass system? Can I just say that they both have the same velocity? No, I can't, because this velocity is going this direction, and this velocity is still going this direction. So this is not an inelastic collision. They are still both moving. So what do I have? I have mass 1, velocity 1 prime minus mass 2, velocity 2 prime. So let's see, what do we come up with? Well, let's see. I know mass 1 and velocity 1, all that information is there. I know mass 2 initial velocity 2 is there. And I know mass 1 and mass 1 velocity prime there. I don't know this one. So what I can do is rearrange this, and I'll have mass 1, velocity 1 minus mass 1, velocity 1 prime minus mass 2, velocity 2 equals, let's see, I'm going to divide by this mass, by mass 2 equals velocity 2 prime, and let's not forget that negative sign. Now what I can do here, just to kind of clean it up a little bit, so it's not so much button pushing and it helps eliminate some mistakes, is I can factor out this mass 1 and just go, let's see, then that'll leave me with what? Velocity 1 minus velocity 1 prime minus mass 2, velocity 2, all of that divided by mass 2, and that's going to equal my V2 prime, my negative V2 prime rather. Now let's put numbers in there. So mass 1 is 1.6, velocity 1 is 4 meters per second. I'm going to leave out the units so it's not quite so cluttered. 4 meters per second, and I'm subtracting its final, which is 3. Make sure that prime is clear. Minus 3, minus mass 2, velocity 2. So mass 2 is this 2.1 kilograms times this velocity 2, which is this initial velocity. Be careful not to put in the negative signs. So if you look up here and you go up and you decide, okay, I'm going to make that a negative and make this a negative, don't come up here and re-put in the negative sign for that velocity. Only let it determine this sign once. It's common error. So let's see, mass 2 is what? 2.1 kilograms. And I get this as negative 1.74, I believe, something like that. Yep, negative 1.74 meters per second. Okay, good, it's negative. I expected a negative value because I expected it to still be going this way. So that's my first error check place, is that if this isn't a negative number, when I crunch all this out, then that means I have it actually going that way. So the negative value is good. All right. So now let's think about the spring. What do we have here? So when I'm moving this way and moving this way, see, they're both in motion. So I have like KE1, like KE2. And I feel like I still have kinetic energy. Yep, I'm in motion. So KE1 prime. And this one is also still in motion, KE2 prime. Make that clear too. So let me ask you this. Do you think that the kinetic energy here and here, the sum of those two, is going to equal the sum of those two? And if not, why, or where do you think it went? I said this is a frictionless surface. So what do you think? Because I kind of feel like what we can do is say something like this, that my kinetic energy 1 plus my kinetic energy 2 is going to equal, let's see, kinetic energy 1 final plus kinetic energy 2 final. But there's something else in there. So shouldn't all of this energy be going into that motion and compressing that spring? Because indeed it is. So potential energy from the spring. So in essence, what I'm looking at is, let's see, my KE, the sum of my KE initial minus the sum of my KE final, because this is just the sum of those two things, KE final, is going to equal, it's the difference in those energies that's going into compressing that spring. That's where that energy went, is going into my potential energy spring. So let's see, I have then 1/2 m1v1 squared plus 1/2 m2v2 squared minus 1/2 m1v1 prime squared plus 1/2 m2v2 prime squared. And that's going to equal 1/2 kx squared. So remember, that's the energy compressing a spring. So I can do something for myself here. The masses won't cancel because I have a spring. So that's the sad thing. When I get here, I can't just make my masses go away, but I can make these 1/2s go away. They all cancel out. So now I can button push this. And so what do I get? I get, let's see, mass 1, 1.6 times velocity 1 squared, 16, plus 2.1 times 2.5 squared. And this comes out to, let's do a different color, 38.725. Now let's do the other one. So mass 1, 1.6 times 9 times 9 plus the 2.1 times 1.74 squared. And that gives me 20.758. Let's see, what are these units? This would be in units of joules for both. So see, they aren't the same. So that does say that I have lost energy, and we used momentum, right? Momentum was conserved, but I have this internal energy component going on here. So what I'm comparing is the internal energy before and after the collision. And then I get that, so now I can take the difference in those two, minus this, gives me 17.97 joules equals 600 Newton meters per meter x squared. So my compression then, let's write it over here, is going to be, I'm going to take the square root, move this over here, divide by both sides, and then take the square root. So I'll get the square root of 17.97 divided by the 600 equals X. So take that, divide by my 600, and then take that to the 1/2. Whoops, didn't like this. What did I do? There we go. And I get it compresses 1.4, so X equals 1.49, or actually let's just go 1.50 centimeters. That's it. So even with the spring in there, it's not as terrifying as it originally sounds. What do? We looked at the velocities before, and then we used conservation of momentum, because there are two systems that are colliding. So if I know this velocity at this snapshot in time, I can use conservation of momentum to figure out the velocity of that one at that point in time. And then we can use energy to analyze it. So we look at the total kinetic energy of both of these things and subtract out the energy that we have here, because that value has to go somewhere, right? And so that value, the difference in those two, well, that was in compressing this spring. So if I take the sum of these and subtract the sum of these two kinetic energies, that gives me the energy that went into the spring. And then I can come down here and relate the difference in those energies to the spring potential energy. And that finally gets me to how far is the spring compressed at this point in time. There you go.